Okay, good morning, everyone. It is my great pleasure to introduce today Young Kim. He is currently a PhD student at Stanford under the supervision of Professor Dan Bonnet. His focus is fully homomorphic encryption, where he focuses in both theoretical and practical aspects of FHE systems. And more specifically, his expertise lies on this discrete version of CKKS variant of FHE. So precisely today, he's going to talk about discrete CKKS exactness from approximate computation. So the floor is yours.
Oh, thank you so much for the introduction. So let me start the presentation right away. So the title of this talk is discrete CKKS. This is combination of like our recent works, like on building discrete systems upon the approximate scheme called CKKS. And in terms of like presentation overview, I would say it's more like telling you a story about how do you start with like noisy approximate computation system and try to build exact computation system. So it will be like kind of a cute math talk, I would say, but also some intuitions on FHE. So I guess most of you here would know what is FHE or fully homomorphic encryption, but let me briefly describe what is this. So this FHE is, in terms of technology, FHE is a member of what is called privacy enhancing technologies, or PETs. So it allows you to compute whatever things you want without sacrificing privacy. So you may compare FHE with different kinds of PET options, including a multi-party computation, or MPC, differential privacy, or DP, trusted execution environment, or TE. And in terms of advantage of FHE, FHE is the only option that provides cryptographic confidentiality together with no interaction property. So as you can see in the table, and so like if you just think about like functionalities of like what FHE do, and it is amazing because like you can do whatever computation you want like without really interacting with others. So it's nice, but the biggest like disadvantage is that it is pretty expensive. So how much expensive? Where let's say you want to do some computation like machine learning, then the computation cost, I would say, is usually like 3 to 4 orders of magnitude compared to like the plain text computation. So that was a brief introduction of FHE. And I would like to describe like a syntax of how FHE works. So the basic example of FHE is where you have a client and a server, and you want to do kind of outsourced computation. What it means is that client has a data which and the client doesn't want to reveal the data to the server or the cloud, but want to do some kind of computation, and therefore they outsource the computation to the server using FHE. And to do this, the client first encrypts their data with FHE and sends the ciphertext to the server. And in the server side, they can somehow compute function f on this ciphertext without really looking into the ciphertext. And then you get an encryption of the result you want, and then it is sent back to the client, and client can decrypt it. And yeah, this is how it works. And I would say FHE is now already pretty mature, like since the first development, and now like started to be deployed, I would say. So for instance, Apple recently introduced visual search in their mobile devices. So how it works is that like think of you have like photos in your iPhone, and like you don't want Apple to really like access all your photos, but like you want to identify any landmarks in the photos, then like Apple uses FHE to like not look into your photo, but like they get the encryption of these photos. I mean, actually encryption of embedding of these photos, and then they identify landmarks in an encrypted form, and then send back to the client. And the user can actually see that, for instance, oh, there's a famous building there, and so on. So this is one example. And the other application is like providing privacy in blockchain. So usually blockchains are very transparent. Like for instance, you get salary inside blockchain, then like your friends or families or whoever can know like what amount you get for salary by blockchain, which is not so great. And FHE is kind of a good solution in this way, that like you can actually like, for instance, hide your salary or like transactions. And compared to like other options that provide this kind of confidentiality, like the ZK snarks, or the zero knowledge proofs are widely used in blockchains, but like FHE provides some good like efficiency in many cases, because you don't really have to like prove your knowledge or something like to provide privacy, but you can just upload your ciphertext. And then afterwards, you can compute whatever transaction functions you want. OK, so now I want to go to like math parts of this presentation. And let me formally define what is FHE. So FHE is an encryption system consisting of an encryption function and a decryption function. So it is pretty much the same as like what you would think of an encryption scheme, but like it is called a homomorphic encryption because because the encryption function is homomorphic. What it means is that let's say you have two ciphertexts, CT and CT prime, and then you can define addition and multiplication over the ciphertext space. And it satisfies these two properties. So first, it should satisfy that decryption of addition of two ciphertexts should lead to addition of the underlying plaintext, and also similar for multiplications. So like since you have addition and multiplication, and these operations are pretty complete, you can compute whatever function as you want, starting from by building like anything as like a combination of addition and multiplication. So at a first glance, this looks pretty strange, because usually if you have this kind of good mathematical properties, then like it is usually insecure. Like if you can add and multiply on like ciphertext, then like it usually makes it easier for you to decrypt the ciphertext. But surprisingly, there has been a construction from lattices, which is a well-known primitive in cryptography, by Gentry in 2009. Like he introduced the concept of bootstrapping, which I'm going to describe later, to make fully homomorphic encryption work. So since the beginning of, the invention of at the beginning of fully homomorphic encryption, there has been like many schemes, like many FHE schemes that like fundamentally and practically improved the performance of FHE. So in the beginning, it was like really slow. Like even like single addition or multiplication took like so much time, and it was not like something you could use in your application. But since then, like all these like developments like improved the performance by like orders of magnitude, and now like the performance is pretty, still far from like plain text computation, but like usable in real world scenario. So the first kind of schemes are called BGB and BFB. So like in terms of functionality, you can regard them as like vectorized operation over some finite fields. So you can imagine like a P is a prime, and they operate on like modulo P arithmetics. And then like later, by the development of like techniques called like GSW and Dukas-Michencio scheme, and upon it, like there was a scheme called the TFHE, which efficiently works on individual ciphertexts, so that this is no longer vectorized ones, but like work efficiently on like bit level operations one by one, and provides fast bootstrapping. And this now serves as a one branch of FHE. And the other improvement was in like changing the plaintext space. So there was a scheme called CKKS, where now they natively work over the real number space R, still in a vectorized format. And since real number arithmetic is so used a lot in machine learning, and since like outsourced machine learning is one of the main application of FHE, like it has been widely adopted since then. Yeah, and in the recent like 2 or 3 years, there was some attempt to like do discrete arithmetic using the approximate scheme CKKS, and that is what I'm going to talk about in this talk today. Okay, so let me now start the math. So I want to keep this very high level, and like I want to give you intuition on like what is going on with these like different schemes, and like especially what discrete CKKS is doing. So I'm going to use an abstraction where like I would just regard lattice arithmetic as just like noisy integer computations. So and I'm going to use a kind of non-standard notation of like putting least significant bits in the left and most significant bits on the right. And these bars will denote integers. And I will place like error E, something like error E there, like inside these long bars to indicate where the message or errors are located. And let me start talking about these noisy arithmetics. So yeah, let's consider you have like 2 integers, x and x prime, and you want to just multiply. So these long 2 bars are just integers, but like the problem is that they are noisy. So what it means is that we want to compute on an integer x, but they are actually x plus e and x prime plus e prime for some small errors e and e prime. Another property is that every multiplication accumulates some additional noise from the least significant bits. So you will be adding more noise after every multiplication. So for instance, if you multiply these 2 integers, then what you would expect is x prime, which is a product of x and x prime, but you would get additional noise, xe prime plus x prime e plus e prime, plus some more multiplication noise. So to get this, you can write the multiplication formula in this way, and you can like group everything instead of x prime, and you can see there's a huge error coming from here. And in particular, since x is as long as the size of the bar, the noise, the multiplication xe prime and x prime e like makes your error bar grows as long as like the original message space, and therefore every time you multiply, like the noise grows like by huge amount. So, and the question of this talk is, how do we design an exact arithmetic from this kind of noisy arithmetic? Please feel free to interrupt if you have any questions, because this notation will be used throughout the talk. So, do you have any questions? on the notation? If not, then I will proceed. Okay, so the first and natural attempt is to completely separate message and error. Also can be called as BFV scheme. And this attempt enables arithmetic over ZP for a smaller modulus P. So this enables modulo P arithmetic, and I'm going to explain how this works. So instead of like treating your message to be like entire integer for this large bar, you can like locate your message in the most significant bit of the integer, so that they are well separated with error in the sense that error is small, and in the LSB, and message is large, and in the MSB. And if you multiply with these, then you still get these huge errors, but your message is the product message is now located in your MSB, and so you still have some separation between message and error. So if you write down as a formula, then we introduce some kind of a scaling factor delta, which puts your message in the most significant bits. And if you multiply these scaled noisy messages, and divide by delta and round, then rounding operates like a cutting error at this point, and you get a product message, noisy product message, which has your product in the most significant bits. And like, okay, sorry. Okay, so if you look at this formula, you can observe that every time you multiply, the error would grow by roughly by the size of the message. And therefore, the error, like E double prime, is always larger than the initial errors E and E prime, and they will like accumulate throughout the computations. And therefore, like in order to provide some exactness of this MSB, this computation is by definition is naturally a bounded computation. What I mean is you can only do a bounded number of addition and multiplication, and that is why we need to introduce a process called bootstrapping. So bootstrapping is a homomorphic operation, which means we compute on ciphertext, and that is an operation that reduces the noise. So let's say you have a noisy message with huge error, and you convert it to another noisy message with much smaller error. So this is the definition of bootstrapping. And then you may wonder how bootstrapping works. Then I can like intuitively describe a high-level idea of modern BFV bootstrapping. So you start with a noisy message with large error, and you modulus switch your noisy message to a smaller modulus. What it just means is that you just cut your bar at this point, and then it will not like exactly cut. So you will introduce additional new green noises in the least significant bit of the shorter noisy message. And then the trick is that you can regard this new short noisy message as if it's a fresh one. So you just like make it longer again. I mean until as long as the original message, and pretend that this is like a fresh message without noise. And the key part is that then now you like evaluate a homomorphic modular reduction, which is essentially homomorphically extracting this MSB from this noisy message, then the homomorphic operation itself would accumulate some noise, but it will be smaller than the initial noise, so that eventually it allows you to successfully bootstrap. Okay, so and the next generation called CKKS takes another approach, which is to just live with the error. So what it means is that, so this scheme is a scheme over real numbers. So an arithmetic is now over reals, and but we will put our message together with the error. So what it means is that we have real numbers m and m prime, and we increase these real numbers by some scaling factor delta. So we somehow like try to preserve some kind of precision, but still these messages will live with the error, like accumulated in the least significant bits. So like you can just think that, well, we have a noisy message which is contaminated from the bottom, and as exactly as in a BFB multiplication, you can multiply these two, and like cut the noise and get multiplication results. Then this enables multiplication over real numbers, because like if you try to multiply these, then and you cut, then you have the same scaling factor as the beginning, and yeah, this gives you some kind of a fixed point multiplication. And if you think of like usual floating point or fixed point arithmetic in the plain text world, I mean where it's not like encrypted world, then you already have like error in some kind of error. So like in some sense this is acceptable, and yes, and this paradigm is just leaving with the error. And so now we don't have error accumulation problem, so we don't need to like bootstrap in the BFB bootstrapping sense. But now the problem is that every time you multiply, you actually cut your LSB, and the bar is actually getting shorter and shorter as you proceed. So like at some point you will have like no space in front of these messages, and then it will like incur some like overflow. So it is also bounded computation, and therefore we need to do some CKKS bootstrapping, which is an operation that homomorphically raises the modulus instead of homomorphically reducing the noise. And like this is kind of I would say this is analogous to BFB bootstrapping, but in the most significant bit version. So what it means is like if you have a ciphertext with short bar, then you extend the bar by raising your modulus, and like raising actually introduces some new green errors, like slightly higher than the initial message. And there you evaluate a homomorphic modular reduction function, which removes the green error, and then you get the extended bar, which is essentially the result of CKKS bootstrapping. Okay, so I described the two schemes, BFB and CKKS, which operates over different error message models. So in BFB, the message was put in the most significant bits, and errors are accumulated from LSB. And while in the CKKS, you put both message and error in the least significant bits and just live with your error. But the next scheme I'm going to talk about is discrete CKKS, which can be regarded as some kind of hybrid between the two. in the sense that you put message somewhere between LSB and MSB, but you still have a clear separation between message and error, so that you can achieve some kind of exactness. Here, first of all, I want to talk about BFB bootstrapping aspect of discrete CKKS. So for simplicity, let's consider encrypting a bit B instead of a large message M. And as in the BFB bootstrapping, we want to somehow reduce the noise of this noisy message, and to write down as a formula the plain text message, the noisy integer can be represented as a scaling factor times bit plus some small error. And if you write this as a real number, then it can be written as delta times x, where x is a noisy bit. So x is near 0 or 1, but pretty close to 0 or 1. And what we want to achieve is to reduce the noise. What it means is that input a number that is close to 0 or 1. We want to also output a number that is close to 0 or 1. But the requirement is that the distance from the target bit should be smaller after this operation. And now this comes to kind of a undergrad level calculus thing, because we do know which real function have this kind of property. So let's say we have a function fx equals to 3x squared minus 2x cubed. Then this function is nice in the sense that it satisfies f0 equals 0, f1 equals 1, and it has vanishing derivatives in around 0, 0, and 1, 1. And you can see that this is exactly the property we want. So if we wanted that, we start with points that is close to 0 or 1, and we wanted to make it closer. And the fact that it has vanishing derivatives, it roughly squares the error away from each point 0, 0.0, and 1.1, and achieving the cleaning property as desired. And I would also consider the property of raising the modulus, because this is kind of a hybrid scheme. So we also need to tackle the problem of the bar getting shorter and shorter. And for this, discrete bootstrapping is now defined as both raising the modulus and cleaning. And cleaning could be achieved by evaluating a good-looking real number function, and bootstrapping will look almost remains the same. But it turns out that we could achieve both at the same time easily by what is called Hermite interpolation, which is a kind of a cleaning interpolation version of usual Lagrange interpolation. But I would not go deep into the details. And one interesting property of this new discrete bootstrapping is that we can evaluate a function on the way for free. So let's say we have our message space is M. Then we can compute arbitrary function from M to M on the way of evaluating a discrete bootstrapping. And this is quite analogous to the framework of the TFHE, the bitwise FHE, because in there they everything operates on functional or programmable bootstrapping, and they combine these to make whatever circuit is you want, and our discrete CKKS bootstrapping provides some kind of a vectorized version of TFHE or DM bootstrapping. And to note it really provides in terms of arithmetic. It provides arithmetic, vectorized arithmetic over some small message space. For instance, the message space is like z to the 8, like modulo 256 operations, and like you can use these to build whatever applications as you want. And this is kind of a fundamental primitive of this discrete CKKS framework. So like,
Can I ask a question of this?
oh sure.
What's the limiting factor here for the message space size?
So basically, what you will be so your functional bootstrapping is basically applying interpolation over the message space. So if your message space gets larger, then so the size of the message space corresponds to the degree of the interpolation polynomial. So like it cannot be like very large. So it grows, yeah, it grows almost exponentially. So you need to like kind of choose a good number that is sufficiently large, but like not so large to be like to make it difficult to be interpolated.
So in practice, you can't really go much larger than this space.
I think z to the 8 is like kind of near the boundary. So like because it's already like degree 256 polynomial, it's pretty okay. But if you go like degree like let's say 1024 or 2048, then it takes too much time. It soon becomes like too much time for this. And like alternatively, we can actually iterate this to get arithmetic. What I mean is like let's say you have like 16-bit arithmetic, then instead of like interpolating over the entire like 2 to the 16 degree polynomial, you could interpolate. I mean, you could divide it into two chunks, like two 8-bit chunks, and operate on it. And usually that is more efficient than like interpolating over the larger space. Okay. And that is actually what I was going to explain in the next slide. So using these, I mean, by representing like large message space as like smaller chunks, you can actually like enable like any precision arithmetic. I mean, with like digit style representation, and you can do like textbook multiplication or like multivariate like style interpolation and so on to achieve whatever arithmetic you want over these digit represented like data, and that is why I called it ALU, and it can be used as a kind of a primitive for any unsigned like integer computations in general. And in particular, like we compared with the other branch, I mean the bit FHE branch in the well-known library TF-HERS. And if you compare like 64-bit operations, different 64-bit operations on and compare with them, it's in terms of amortized latency, like I mean this approach is like 2 to 3 orders of magnitude better. But like in terms of the latency, it's much worse. But like there were some even recent developments that even reduces the latency close or even better than bitwise FHE.
What's the intuition for why the amortized latency is much better in your case?
So TF-HE is a kind of a completely different branch I didn't really mention in the talk. And like these CKKS and VFB, and these schemes are vectorized schemes. So you can think of more like a GPU, but the entire latency is slow. And TF-HE is not vectorized scheme, so it works on individual ciphertext. I mean individual like messages. So they are pretty fast. So there has been always a trade-off between like these non-vectorized FHE and vectorized FHE. I mean the trade-off between latency and amortized latency. but like until now, like there were no good ways to emulate what they can do in bitwise FHE, because like in bitwise FHE, they had a very fast like small integer style arithmetic, whereas like in the corresponding vectorized world, we didn't have one. Like we had more like interpolations over finite fields, so which are not so great usually for these small integer arithmetic, and like this kind of like approach lets you emulate, I mean, the vectorized version of what bit FHE or TFHE could do. So
oversimplified, would it be more or less correct if I oversimplified and just said that the setup is slower with your approach, but once the setup is done, things run faster? And that's why you know, the latency is slow, but you get better amortized time overall?
So I would say intuitively it's like a comparison between CPU and GPU. So for individual like GPU, each thread is like much perform poorly than like CPU thread, but like it has like many threads. So the amortized latency is always better. So
it depends on the application, right? If the application allows you to vectorize the computation, then CKKS would be superior because you don't care about the latency much.
Okay.
And then the scheme on the left, they are more optimal to really deal with the single ciphertext, right? On the right, you need to do this big thing anyway, but luckily you have the opportunity to pack a lot of messages into one ciphertext. So that's
Okay.
what usually happens.
yeah, and you can play a little bit more, and like for instance, you can try to run like a residue number system like homomorphically inside, inside FHE, and that essentially provides like arbitrary modulus arithmetic, and you could achieve you can achieve like any like Z M arithmetic for whatever integer M you want. So yeah, this is more like an example, and also like this allows you to connect CKKS and discrete CKKS, which I mean by like CKKS operates on like floating point or fixed point numbers, and discrete CKKS operates well on like small size integers, and we have efficient conversions between the two, and this pretty fits well with the quantization framework in machine learning, where you like instead of like operating on like huge floating point numbers, you like look up for like short size like 4-bit or 8-bit integer, and so this naturally fits the framework and gives better efficiency. And like although this kind of framework is like very new, like there were already like a bunch of works in the last 2 years. I wanted to like just let you know like those big from the beginning, the start, like there are a large attempts to like build a better lookup tables. I mean, which is essentially better functional bootstrapping. And I mentioned like attempts on like building integer arithmetic system upon this framework, and many applications were there too. So this is the end of the talk, and thank you so much for listening to my presentation.
Are there any questions?
Let's stop the recording here.
Okay. Yeah.
And then we can have any questions.